So, before we begin, I would like to, on behalf of the DIA, to acknowledge the traditional owners of the individual lands on which we're all gathering tonight and all First People nations on the land now known as Australia. The DIA respectfully recognises elders past, present and future. We celebrate the innovation, creativity and ingenuity of the world's oldest living creative culture. So welcome to everyone that I'm seeing here tonight, our wonderful Design Institute members that are joining us, as well as a very special welcome to some of the attendees tonight who are perhaps future members of the Design Institute of Australia. For those of you who I've not met, my name is Dr. Nathan James Crane and I am the chair of the SANT State Council. It's absolutely incredible to see such great support for our programs and events. As I mentioned before, we have about 200 attendees tonight, and the SANT Council really wanted to create a series of public talks that cover ideas and discussions relevant to all disciplines represented by the DIA. Tonight is the first of our public series, which we hope will be able to continue to engage and inspire our members. So a little bit about David before I hand over. It's a long introduction, but one that is very impressive. So I wanted to make sure that I canvass David before I hand over the floor. Dr. David Briggs is a painter and teacher of life drawing, anatomy, painting and colour for painters at the National Art School, the Julian Ashton Art School and the University of Technology, Sydney. His publications include his outreach websites, The Dimensions of Colour and Colour Online, and a chapter in each of the Routledge Handbook of Philosophy of Colour and the Springer Encyclopedia of Colour Science and Technology. David is Vice President, New South Wales Divisional Chair and Colour Education Officer of the Colour Society of Australia and is a committee member of the International Colour Association, or AIC, and Inter-Society Colour Council Colour Literacy Project, which is an international educational initiative to provide age-appropriate colour curricula and state-of-the-art resources for teachers across science, art and industry. David has been teaching classes and workshops on colour for painters for 20 years and has also written and presented for the Art History and Theory Department of the National Art School, Sydney, on the history of colour theory and practice. He gave an account of his unique approach to colour education for painters as an invited speaker at the workshop presenter and as a workshop presenter at the ISCC AIC Munsell Centennial Symposium in Boston in 2018. And of course, tonight, in an exclusive talk, David is discussing his latest research into understandings of colour. This is the first public talk to canvass the ideas covered in his new work, which will be published in the coming weeks. David will present his talk for us tonight before we open up for questions at the end. So please do hold on to those or post them in the chat and we'll get to them. It's with great pleasure that I now hand over to David to begin his presentation. Thank you, David.
Thank you, Nathan.
I'd very much like to thank the Design Institute of Australia for inviting me to speak tonight to start off their colour series. I'd especially like to thank Catherine Piergros for extending the initial invitation to speak and Nathan and Georgina for organising the webinar tonight. The invitation was very timely because I've just had a two-part paper on the fundamental elements of colour accepted for the Journal of the International Colour Association, or AIC. Part 1, which I'll concentrate on tonight, presents an extended answer to the question what is a colour by reviewing the connections between colour stimuli, colour perceptions and colour measurement, while Part 2 focuses on an analysis of colour perception, exploring the main modes of colour appearance, for example as belonging to objects or to lights in various ways, and the standard perceived colour attributes, hue, lightness and so on, and their interrelationships. Both parts will appear in a special issue of the journal devoted to contributions from the ISCC AIC Colour Literacy Project, very patiently edited by Robert Hirschler and due out next month. The AIC journal is open access and you'll be able to download all of the papers as PDFs from the link shown here. It might seem reasonable to assume that most colour educators are in broad agreement about the fundamental facts concerning colour, and would disagree, if at all, only about the best ways to address those agreed facts. But my impression, based on more than 20 years of discussions, both in person and online, is that this perceived agreement is an illusion that would be dispelled very quickly the moment any sizable group of colour educators began discussing colour in detail. Extensive disagreement exists, not just stemming from simplistic traditional red, yellow, blue colour theory, but also in relation to our current scientific understanding of many fundamental aspects of colour. While legitimate differences of opinion exist about some details, my aim in these papers was to provide an account of the fundamental elements of colour according to the scientific consensus expressed or implied in the definitions of the International Lighting Vocabulary, or ILV, of the Commission Internationale de l'Éclairage, or CIE, except where additional constructs are explicitly added, such as from the Natural Colour System, or NCS. In doing so, I've drawn on insights, explanations and illustrations I've developed over more than 20 years of teaching courses on colour for adults mainly with an art or design background, and 15 years of creating online resources on colour. The papers build on some earlier presentations, including those I gave for AIC 2021 and AIC 2022. Founded in 1913, the CIE is the organisation responsible for the international coordination of technical standards relating to colour and light. The CIE developed the framework of modern colorimetry from the earlier 20th century through to the present, and established numerous colour spaces that form the basis of colour management and colour technology, including the horseshoe-shaped 1931 XY chromaticity diagram that you may have encountered in various contexts, C-Lab, the lab space familiar to you from Photoshop, the luminous efficiency function that is the basis of lighting standards, various standard light sources such as D65, and various standard formulae used for quantifying colour differences in industry. The CIE International Lighting Vocabulary, first published in 1938 and revised periodically up to the current edition published in late 2020, gives definitions of nearly 1,400 terms and is by far the most comprehensive and authoritative source available on the terminology of light and colour in science and technology. The CIE ILV defines the word colour in two distinct senses, the perceptual and the psychophysical or colorimetric. I'll return to colour in the psychophysical sense towards the end of this talk. Colour in the perceptual sense is defined as a characteristic of visual perception that can be described by attributes of, and I quote, hue, brightness or lightness, and colourfulness or saturation or chroma. That might look like they're giving alternative names for just 3 attributes, but those are actually 6 differently defined attributes of colour. We'll look at these definitions individually in a moment, but for now I'd just like you to note that colour and its attributes like hue, lightness, etc. are all defined as characteristics of visual perception and not as physical properties, as you might have expected. These 6 attributes and their definitions are based on work published in the late 1970s by Robert W. G. Hunt, and have been essentially stable from the 4th edition of the CIE ILV, published in 1987, through to the current edition, published in late 2020. But despite this long period of stability of the standard nomenclature, I've observed over many years that the distinctions between some of these CIE-defined attributes are often poorly understood even among very experienced colour educators, and indeed that these distinctions sometimes seem much easier to grasp for students who are new to the subject than for those with firmly entrenched ways of thinking about colour. Several factors could have contributed to the delayed reception of these concepts in colour education. The CIE ILV has always been expensive and relatively limited in distribution in hard copy, and its definitions only became freely available in 2012 as the online eILV. In addition, the terse verbal and mathematical definitions in the ILV can be difficult to understand for non-specialists, and I'm hoping that the insights, explanations and illustrations presented in my papers will lead to a more widespread understanding of these standard attributes. Just 3 attributes suffice to describe colours as long as we consider only a single mode of colour appearance. For example, the colours perceived as belonging to light-reflecting objects. For these colours, the 3 CIE-defined attributes of hue, lightness and chroma suffice to specify a colour. Hue, represented by the position around the colour circle, is described in the Munsell system in relation to 5 what are called principal hues: red, yellow, green, blue and purple, and in various digital colour spaces as a hue angle. Lightness, which is also known as value, grayscale value or tone, refers to the scale between black and white through various greys, and this is specified in the Munsell system in terms of Munsell value, which ranges from 0 to 10, and in CLAB by L star, which ranges from 1 to 100. And finally we have chroma for in effect the intensity of a colour perceived as belonging to an object. Chroma has often been equated with saturation, but in CIE terminology, saturation is defined as a separate attribute of colour. An alternative set of 3 colour attributes that can be used to specify colours of objects are the attributes of hue, blackness and chromaticness used in the natural colour system or NCS, as shown on the right. These attributes stem from thinking of colours of objects as having resemblances to, or perceptual components of, black, white and pure colour, adding up to 100. In standard CIE terms, chromaticness, which increases towards the right-hand corner, is in effect chroma relative to the maximum chroma perceived to be possible for objects of a given hue. But blackness, or perceived black content relative to pure black, which increases towards the bottom left corner, is an entirely distinct attribute of colour not currently treated in the CIE ILV. Both hue, lightness and chroma, and hue, blackness and chromaticness only really work for colours perceived as belonging to objects. Lightness, or grayscale value, for example, is our perception of how much of the light falling on an object that it reflects compared to a white object. For example, a sheet of white paper is perceived to remain high in lightness, to be white, even as we reduce the brightness of the light reaching our eyes from it by putting it in a shadow area. Colours perceived as belonging to light exhibit brightness, which has an open-ended range, but not lightness or grayscale value, or blackness. For example, think of a view of city lights. We see these as varying in brightness, but we don't normally perceive the brightest light as being white and all of the other lights as shades of grey or as having a black component. Now it might occur to you that right now we're perceiving lightness or grayscale value and blackness on a light emitting screen. But the point here is that we normally read a screen as an illuminated page rather than as a primary light source, which it is physically. What matters is that we normally perceive the screen as if it was an illuminated page. Both lightness and chroma are defined in the CIE-ILV in a way that restricts them to areas perceived as being illuminated, that is, as illuminated objects rather than light or light sources. Other colour attributes, including brightness, come into play when we wish to describe colours perceived as belonging to light itself, including 1. Light perceived to be falling on objects, or 2. Light reaching the eye, either directly from a primary light source or reflected or transmitted by objects. Therefore, more than 3 attributes are needed to fully describe the appearance of illuminated objects, which involves colours in more than one mode of colour appearance. In this image, we perceive a cube having a uniform orange colour belonging to it, as if it were painted all over with the same orange paint, having a constant hue, lightness and chroma, corresponding to a Munsell notation of about 10R614. For actual objects, the attributes of lightness and chroma exhibit a tendency towards stability or constancy under varying viewing conditions, especially varying intensity of the same illumination, which is why they are perceived as belonging to an object. At the same time, areas A to B to C appear progressively higher in brightness and colourfulness. This is the perceptual result of their sending progressively greater amounts of light to the eye, evoking progressively stronger responses at the level of the light-sensitive retina. Similarly, although we perceive the lighter coloured areas of the floor as being white things, that is, as objects having a white colour of uniformly high lightness belonging to them, the corresponding areas send light of a wide range of intensities to the eye, which we perceive as a wide range of brightnesses. This variation in brightness and colourfulness is perceived as being imposed by the illumination rather than as belonging to the objects themselves. Brightness and colourfulness describe the appearance of the light reaching our eyes from different areas of an object, in contrast to the lightness and chroma, which describe the colour perceived as belonging to the object. The CIE-ILV describes an object colour as a colour perceived as belonging to an object, where the word colour links to the entry for colour in the perceptual sense or perceived colour. So an object colour, as defined by the CIE-ILV, is a visual perception perceived as belonging to an object. Although they are perceptions, we perceive object colours to be located outside us in objects themselves, as in the uniform black, white and orange object colours that we perceive to be located in the tiles and cube depicted in this image, even though, and this bit is in italics, even though these objects are physically non-existent. This last observation can help students to accept that the colours that sure seem to be located in real objects, including the real objects around you now, are similarly not actually located in those objects, but are perceptions that we project onto those objects. However, as philosopher Clyde L. Harden famously said, coloured objects are illusions, but not unfounded illusions. If these were actual objects, we would undoubtedly find that they differed in the physical property of spectral reflectance. The spectral reflectance of an object is the proportion of light of each wavelength that the object reflects. when we can freely examine an object in daylight, this colour that we perceive as belonging to the object is usually a very good indication of its overall spectral reflectance. I'll elaborate on exactly what I mean by overall shortly. So within the rectangular image on the left, we perceive a pattern of orange, black and white object colours, which are shown bottom right. Yet, within the same rectangle, we also perceive a pattern of illumination, that is, a pattern of light perceived to be falling on the objects, comprising areas of light and shadow, as I've shown top right. Colours perceived as belonging to illumination, called illumination colours, can be described in terms of hue, brightness, and either colourfulness or saturation, though the illumination in this scene is perceived as achromatic or white light, lacking hue and saturation or colourfulness, and varying only in brightness. Notice that we experience these perceptions of object colour and illumination colour superimposed in the same rectangle, as if the object colour is seen through the illumination. But how do we perceive, for example, which areas are dark because they're occupied by dark things, and which are dark because they're dimly lit? It may seem to us that we directly detect these variations in illumination and object reflectances, but there's no way for our eyes to do that. Instead, our visual system automatically, instantly and seemingly effortlessly parses or resolves the scene into superimposed perceptions of spectral reflectance as object colour and of illumination. It's only because this remarkable capacity of our visual system exists and is generally very effective that we perceive objects as having a relatively constant and seemingly intrinsic lightness and chroma belonging to them, and not just constantly varying brightness and colourfulness. This ability to automatically and unconsciously parse a scene into colours relating to illumination and objects imparts a degree of constancy to our perception of object colour under coloured illumination. We're likely to attribute the overall pinkish colour of this image to the illumination rather than to the objects, and so to perceive some white or grey object colours through this pinkish illumination. This ability is assisted by the quite distinct capacity to adapt to the colour of the illumination, which would cause the whole scene to appear less pinkish than it would otherwise. Nevertheless, despite this ability, our ability to distinguish objects according to colour is reduced under illumination that appears coloured and diminishes to zero under monochromatic light. Our perception of colour has a multi-layered quality that is rarely appreciated. Viewed normally in what is called distal or constancy mode, we have these two superimposed perceptions of object colours and illumination colours. But we can also view the scene in what is called proximal or painter's mode as a flat array of patches of light, the way an impressionist painter might look at the scene. Viewed in this way, the light reaching our eyes throughout the field of view exhibits a third set of colours that can also be described in terms of hue, brightness, and either colourfulness or saturation. The sixth attribute listed in the CIE-ILV definition of perceived colour is saturation, which is defined as the colourfulness of an area judged in proportion to its brightness. Now, the only way for the light from an area to appear less colourful while maintaining its brightness is for it to appear more whitish. So saturation may also be described as the perceived freedom from a white light component of the light from an area. That is, saturation is the perceived proportion of the chromatic component of a light out of the total of its chromatic and achromatic, or coloured and white light, components. So here the light from areas A to B to C increases in colourfulness in step with its brightness, which amounts to saying that it does not become either more or less whitish as it gets brighter, so it stays the same saturation. This relationship holds within limits when light of the same spectral composition varies in intensity, or as here, where a uniform object is illuminated by the same light at varying intensities. I also discussed one additional colour attribute called Brilliance that doesn't currently appear in the CIE ILV, but which is related to the attributes of blackness and saturation. What happens to the colour of an object in a given setting if we increase or decrease the intensity of the light coming from it without changing its spectral composition? If a light stimulus of fixed spectral composition increases in intensity from 0 to very high in relation to its surroundings, it passes through a consistent series of stages, appearing black until a black threshold is reached, and then passing through decreasing degrees of blackness to a point of 0 blackness, and then goes on to appear fluorescent or fluorescent looking, and ultimately self-luminous. The circle on the right face of the cube illustrates this sequence. At low intensity, the same as for the circle on the left face, the circle on the right exhibits a high degree of blackness. At a certain intensity relative to its white appearing surround, the circles on all three faces exhibit approximately 0 blackness. At a somewhat higher intensity, the same as for the circle on the top plane, the circle on the right appears fluorescent or fluorescent looking. At a much higher intensity relative to the environment, the circle appears self-luminous. The brightness at the point of 0 blackness, at which the area appears neither blackish nor fluorescent, varies depending on the hue and saturation of the light. This introduction to the attributes of perceived colour was the first thing I wanted to get across tonight. The remainder of the first paper explores the connections between colour stimuli, colour perceptions and colorimetry, in order to illustrate how colorimetric specifications are purpose-built to capture precisely the perceivable overall spectral properties of lights and objects that we perceive as their colours. This was written partly in response to certain misconceptions that have gained traction in some circles, stemming from demonstrations of colour inconstancy, sometimes called optical illusions, that human colour perceptions do not relate to spectral properties or to colorimetry. But the discussion will hopefully also be of more general interest for its bearing on human colour vision, the rationale behind colorimetry, and the fundamental question of what is a colour. This section begins with a discussion of colours of light. We all know that Sir Isaac Newton showed that the reason why light forms what he called a spectrum when it passes through a prism is because it is broken up into a series of components, we would now say different wavelengths, that appear different colours. Yet when we see a light compounded of different wavelengths, we don't experience multiple colour perceptions corresponding to these multiple components. We see a single colour. Crucially, Newton showed that the colour of an isolated light can be predicted from the overall balance, or what he called the centre of gravity, of its spectral components in a two-dimensional circuit of directions of bias relative to white light, which he explained with his famous colour circle. The hue of an isolated light can be predicted from the direction of bias of the center of gravity relative to white light, and what he called the fullness or intenseness of the color, or its distance from whiteness, now called saturation, can be predicted from the amount of bias. Another way of saying this is that the color of an isolated light is the way in which we perceive the overall balance of its spectral components relative to that of light perceived to be white, such as daylight. So whitish orange as the color of an isolated light is the way in which we perceive an overall balance of spectral components biased in a certain way relative to daylight. And white, as the color of an isolated light, is the way in which we perceive an overall balance of the same spectral components similar to that of daylight. By this principle, spectral orange, the saturated orange we perceive in the spectrum, is the way in which we perceive a very strong bias in the direction of certain wavelengths relative to daylight, rather than a property present in those wavelengths themselves that our visual system detects. A saturated orange light might consist of those orange appearing wavelengths, but it might also contain little or no light of these wavelengths. For example, the saturated orange spot Y at top right on your screens emits relatively little light of such wavelengths. Daylight is defined as the visible part of global solar radiation, meaning combined direct solar radiation and diffuse sky radiation. Notice that the spectral power distribution representative of daylight, D65 in the middle here, is not flat throughout the spectrum as you might assume, but has a broad low peak in the short wavelength part. CIE illuminant E on the right, which does have a flat spectral power distribution, appears somewhat pinkish as an isolated light. You might have received the impression that we perceive daylight as white light because our visual system detects equal amounts of all wavelengths. It doesn't. It perceives daylight as white light because it is attuned to perceive this somewhat uneven spectral distribution as white. It's remarkable that throughout our lives, our visual system continually attunes itself to compensate for the physical changes occurring in the eye, so that typical daylight continues to be perceived as colourless or white light. This adjustment occurs very slowly as our lenses turn brown with age, and relatively rapidly when we get new ones. It makes sense intuitively that it would do this because, as we saw earlier, the more coloured the illumination of a scene appears, the more difficulty we have in distinguishing objects according to their colour. And so being attuned to perceive daylight as lacking hue maximises our ability to distinguish objects by their colours under typical natural conditions. We now know that Newton's directions of perceivable spectral imbalance form a two-dimensional circuit because our colour vision depends ultimately on the responses of three receptor types called L, M and S cone cells. The often expressed idea that our cone cell classes work by individually detecting long, middle and short wavelengths, or worse, by detecting red, green and blue wavelengths, is incorrect. Our S cone cells respond to a relatively narrow range of short wavelengths, mainly those that appear violet and blue, but our L and M cone cells respond to all and almost all wavelengths of light respectively. Also, the specific wavelength of a light hitting a cone cell affects the probability that the cone cell will respond, and thus the strength of the overall response of that cone cell class, but the cone cell provides no information on the specific wavelength of the stimulus. What is true is that the three cone cell classes divide the visible spectrum into long, middle and short wavelength bands, in each of which one cone cell class responds more than the other two. Comparison of the responses of the cone cell classes provides information not about the individual wavelengths present, but about the overall balance of radiant power between these three broad wavelength components of the light. This comparison occurs in the retina by the process of cone opponency. Some neurons compare M cone and L cone outputs to form an L versus M cone opponent signal, while other neurons compare the S cone output to the combined outputs of the L and M cones to form an S versus LM cone opponent signal. The L versus M and the S versus LM cone opponent signals create a 360-degree circuit of possible combinations that we ultimately experience as the circuit of hues. But the red, yellow, green and blue hue perceptions mentioned in the CIE definition of hue do not correspond to these cone opponent axes, and how they arise remains disputed. The role of our cone cell types is widely covered, if somewhat misrepresented, in popular accounts of colour vision, but the equally important process of cone opponency is much less commonly discussed, leaving a gap that's currently filled by a collection of inventive but misguided speculations about cone signal processing that I described a few years ago in a piece called The YouTube Theory of Colour Vision. It's by means of this combined cone and cone opponent system that we can detect variations in the overall balance of radiant power in relation to a circuit of directions towards long, middle, short, and long and short wavelengths respectively. So we can now elaborate slightly on Newton's discovery that the colour of an isolated light is the way in which we perceive the overall balance of its spectral composition relative to daylight by saying that overall here means at the level of its long, middle and short wavelength components as detected by the human visual system. Now, of course, perceived colours can be influenced by a variety of factors in addition to the spectral properties of the stimulus, as acknowledged in Note 1 to the CIE ILV definition of perceived colour. Nevertheless, despite the importance of these other factors, it would be going too far to deny a connection between colour and spectral properties. It's quite reasonable to say that in many ordinary circumstances, variations in the spectral composition of light at the level of its long, middle and short wavelength components are detected by the human visual system and perceived as different colours. This, of course, is why we're all looking at machines that work by emitting different mixtures of long, middle and short wavelength light. So what about object colours? As with colours of lights, our perceptions of object colour are not based on instrumental measurements, but on the responses of the human visual system, and are therefore shaped in part by the characteristics of that system. Since we can only perceive spectral reflectance at the level of its three main spectral components, the colour we perceive as belonging to an object when it's freely examined in daylight is the way in which we perceive its overall spectral reflectance. Overall, again, meaning at the level of its long, middle and short wavelength components, as detected by the human visual system. The hue of the colour is our perception of the direction of bias of this overall spectral reflectance. The chroma is our perception of the amount of bias of this overall spectral reflectance, and the lightness is our perception of the proportion of light that the object reflects, as always subject to the usual individual and environmental effects on colour perception and the workings of the human visual system. Notably, the responses of our visual system taper towards each end of the spectrum, so wavelengths near these extremes have a decreasing influence on our perception of colour. Colorimetric specification of light and objects can be an area of confusion in the broader colour community, and I've sometimes encountered the view that colorimetry is all very well for technology but has nothing to do with human perception. In fact, colorimetric specifications of lights and objects are purpose-built to represent for practical purposes just those physical differences that we perceive as colour differences by ignoring physical differences that are not perceivable to human colour vision. You may have encountered the CIE XYY diagram previously in various contexts, especially in comparing the triangular gamuts of different RGB colour spaces or different devices. It's not the latest, but it's still the most familiar descendant of Newton's colour circle. As was already implicit in Newton's circle, physically different mixtures of spectral components can evoke the same perceived colour if they have the same centre of gravity or overall balance of spectral components. The three spectral distributions on the left here appear white as isolated lights. CIE illuminant D65, representative of noon daylight, CIE illuminant F7, representative of a fluorescent illumination that matches D65 in colour, and a specific white LED screen adjusted to match these illuminants. Despite their physical differences, these three spectral distributions match as isolated lights because they have the same overall balance at the level of their long, middle and short wavelength components as detected by our combined cone and cone opponent system. Location in this XY chromaticity diagram represents this overall balance of wavelengths called chromaticity, given the necessary assumption of a mathematically defined standard human observer, and our three lights would all plot at the same point marked D65. A colorimetric specification of a light represents a class of physically varied lights having a common disposition to evoke a perceived colour, in the sense that physically different lights having the same colorimetric specification would be expected to match in perceived colour when viewed under the same conditions. Thus, a colorimetric specification of a light may be said to quantify what Newton called colours in the rays, meaning the light's power and disposition to stir up a sensation of this or that colour. Our three lights have a common disposition to evoke this or that colour. A colorimetric specification does not, however, correspond to a single perceived colour. Our three lights should match in perceived colour in the same viewing environment, but this matching perceived colour would differ as this viewing environment differs. For example, all three of our lights would look somewhat pinkish in a predominantly green viewing environment. As note 1 to the definition of perceived colour implies, it's impossible to predict the perceived colour of a stimulus based on its spectral properties, irrespective of viewing conditions and other considerations. Colorimetric specifications are not intended to predict perceived colour, irrespective of viewing environment, and their failure to do so is not a failure of colorimetry if the rationale of colorimetry is properly understood. Luminance is a colorimetric measure of the intensity of a light from the point of view of the human visual system. But like chromaticity, luminance tells us what a light will match, but not how that light will appear. The curve on the left, showing the responsiveness of the visual system of a standard human observer to different wavelengths, is called the luminous efficiency function. Luminance is the physical power of the light weighted wavelength by wavelength by this function. Physically different lights having the same luminance would be expected to match in brightness if their brightness is compared in certain ways, notably by showing no flicker when alternated very rapidly, or by finding the point at which they exhibit a minimally contrasting border. But luminance does not tell us how bright a light will appear. These matching lights would vary in brightness depending on the viewing environment, appearing brighter as the environment has lower luminance. An important complication to the concept of luminance that I discuss in the second paper is that if the two lights agree in luminance but differ in colour, they might be perceived to differ in brightness when compared by other methods. Colorimetry of objects involves colorimetric specification of the light reflected by the object under a specified light source, normally a standard daylight illuminant. For an object that reflects all wavelengths equally, the XY chromaticity of the light it reflects is the same as that of the illuminant. And other chromaticities result from various directions and degrees of bias of the spectral reflectance at the level of its long, middle and short wavelength components. Specification of this reflected light can be plotted in a three-dimensional colour space CIE XYY, formed by adding to the XY chromaticity diagram the third dimension Y, representing the relative luminance of the light reflected compared to a reference white. Granted the necessary assumptions of a standard observer and a specific daylight illuminant, CIE XYY values represent for practical purposes the human perceiver dependent overall property of an object's spectral reflectance that we perceive as the colour of that object in daylight, which is the colour that we tend to think of as the seemingly intrinsic colour of the object. Each chip in the Munsell system, representing a specific hue, lightness, value and chroma, is manufactured to embody a CIE XYY specification of the light that the chip would reflect under a specified daylight illuminant. Each of these XYY values represents a class of physically different spectral reflectances of objects that would match in colour to the standard observer under this illuminant, and for practical purposes would be expected to appear essentially the same hue, lightness and chroma to a colour normal observer when freely examined in daylight. I mentioned at the start that the CIE ILV defines the word colour in two distinct senses. Along with colour in the perceptual sense or perceived colour, the ILV also defines colour in the psychophysical sense as a specification of a colour stimulus in terms of colorimetric values. When we speak of colour measurement, colour difference formulae, many colour spaces, and the 16.7 million RGB colours on our screens, we're using the word colour in this second sense. In defining two senses of the word colour, the CIE ILV in effect acknowledges that we may wish to use the word colour either for our perceptions of colour or for the measurable properties of lights and objects that dispose them to appear this or that colour. Colorimetric values specify the perceivable overall spectral properties shared by physically varied lights and objects that dispose them to match in colour to the human visual system. In terms of Hardin's quote, coloured objects are illusions but not unfounded illusions, psychophysical colour specifies for practical purposes the human perceiver dependent properties of lights and objects that our illusions of object colour and other perceived colours are founded on. My second paper focuses on colour perception in greater depth, exploring the main modes of colour appearance and the various perceived colour attributes and their interrelationships. Part 2 is the longer of the two papers, and I'll only try to show a selection of the illustrations tonight. Here we see examples of some of the main modes of colour appearance. We see various object colours which can be subdivided into surface colours of opaque objects and volume colours of transparent and translucent substances such as seawater, and an illumination colour of white daylight. And here we see different illumination colours of light perceived to be falling on an object with a uniform object colour. And this one illustrates a discussion of the interconnections of brightness, colourfulness and saturation and chromaticity. In this illustration, I'm addressing the distinction or relationship between chroma and saturation, which are very often confused. A vertical column of digital swatches of uniform chroma in the Munsell system can be seen to range from lighter swatches emitting a large amount of relatively whitish light to darker swatches emitting a smaller amount of less whitish or relatively more chromatic and thus more saturated light. Swatches exhibiting similar saturation lie along lines that radiate from near the 0 point on the value scale, in contrast to the vertical lines of uniform chroma. For example, swatches A, B and C all exhibit similarly high saturation. They all emit a similarly pure orange light, but vary considerably in chroma. The dimension called saturation, or S, in the widely used digital colour space HSB, which you'll know from the colour picker in Photoshop, is a simple measure of saturation in the sense defined by the CIE, but relative to the maximum saturation possible for digital colours of a given hue. Image areas A, B and C here have the same HSB saturation, and that relationship was used, of course, to paint the cube here. The diagram on the left shows how readily fields of uniform hue and saturation and varying brightness are readily perceived as uniformly coloured objects under varying illumination, provided that their arrangement is consistent with this interpretation. These sequences of colours follow vertical lines in CIE XYY space, but radiate from near the origin in hue value chroma spaces such as Munsell and CLab. Somewhat surprisingly, they seem to radiate for most of their length from a point a bit below 0 in these spaces, which is related to the way the lightness scales of these spaces are defined. This one is from a discussion of how colours of 0 blackness, which trend close to the top of the Munsell colour solid, vary greatly in lightness depending on hue and saturation, being high in lightness for all whitish colours, much darker for saturated blues, for example, and in between for saturated yellows. And this illustrates the complication to the concepts of brightness and lightness related to chromatic intensity that I mentioned earlier. In both the Munsell system and CLab, the lab space you know from Photoshop, swatches of the same lightness by definition have the same luminance. So if we look at any horizontal row of swatches, such as the lightness 50 row here, they all have the same luminance, but we might easily judge the high chroma red to be brighter than the grey of the same L, and we might judge it to match the lightness of the 60 grey or even higher. And yet if we place the L60 grey alongside the high chroma red, I think we can see that it would need to go darker to reach the point of minimally distinct border with the red, even though the red has a sort of glowing appearance. I discuss in the paper how this perception of extra brightness and lightness associated with high chroma swatches may relate to them being unusually high in relative luminance for their hue and saturation in relation to the gamut of familiar object colours. And these illustrations are from the discussion of the attribute of hue, which includes an account of various simple hue circles based on different organising principles. I'd like to thank my students and my many colleagues over the last 20 years, including the colour literacy team, for their feedback on my evolving attempts to explain the concepts discussed in these two papers. I'd especially like to thank Robert Hirschler for his feedback and his patience as an editor, and Professor Mark Fairchild for very kindly agreeing to provide comments on both papers in addition to those of the anonymous reviewers. As I said, my two papers will be available in the forthcoming special issue of the Journal of the AIC on contributions from the Colour Literacy Project team, so you'll be able to download those if you'd like to read more about any of the things I've talked about tonight. You can see the work of the rest of the team in the other papers in the volume, and on other things, including forums, web pages, and various colour concepts and misconceptions, and a series of eye-opener exercises for teachers at the link shown lower right. You can see more of my own work on my website, The Dimensions of Colour, which I worked on mainly from 2007 to about 2017. And there's an index of links to my more recent work on a page towards the end of that site. My other website, Colour Online, is a collection of more than 500 links to useful websites, texts, videos, software and forums, and along with the two papers is my other main tangible contribution to the colour literacy project so far. My boss at the National Art School would kill me if I don't mention my online colour course there, which consists of 8 3-hour live online classes with time for questions and discussion, plus optional practical exercises that can be done in between classes. There are 2 more terms left this year, each with a limit of 12 students, and enrolments are already open on the NAS website. And finally, I'd like you to know about the AIC study group on arts and design, which you're more than welcome to follow on our new Instagram account. And of course, there's the Colour Society of Australia, of which I'm past president, vice president, and New South Wales divisional chair. We're a 100% volunteer-run, not-for-profit organisation with an active program of live events and free webinars on all aspects of colour, including various kinds of design, art, science, philosophy and education. And I'll finish by mentioning our national conference coming up on October 12 to 15 in Western Australia, which will be a hybrid in-person online event. So stay tuned on the CSA website and social media for more information on that and for our
Thank you
other
so much,
upcoming
David. Passing
webinars
to you,
and events.
Nathan.
Thank you, Georgie, and thank you so much, David. It's always incredible just to see, I suppose from a designer's point of view, often, we obviously talk color theory, but it's often such an intuitive thing that we are drawn to pull together. And so it's just fantastic to see the science and the physiology behind color as well. I did want to open the floor for the last couple of minutes to see if there were any questions that we had for David while we have him and his expertise with us. Is there anyone that has a question? I'll check the chat line as well, but please feel free to unmute yourself and to pop up on screen and ask a question now. Mike and Glenna. So Mike, go to Mike first. Oh, Glennis. You've got a raised hand. Did you have a question for David?
She might just be waving.
Might just be waving. I did have a quick question for you, David, which was whether, everyone has a favorite color, and that's always a question. So I was just talking to my nephew last week, what's your favorite color? Is there anything from a physiology or a scientific perspective that draws individuals to resonate with a particular color? Is that something to do with the way we perceive those colors, or is that more a psychological association with that color that makes us, I suppose, have a favorite color?
I don't know. Do you have a favorite color, Nathan? Or
I do. So I suppose my favorite color, like in a basic sense, is purple. But more specifically, if you ask me my designer answer, would be an aubergine. I suppose, like a really deep purple.
Look, I don't really know that I've got a strong opinion on that.
No, that's curious. I just was wondering, whether in the research there was some sort of crossover between people perceiving colors in a particular way, and then why we like those. Maybe it does, something in our brains. I'm not sure. Maybe that's something for us to look at. Sarah, I can see your hand is raised as well.
Yeah, I've got a question for David.
Fantastic.
So David, when I see the center of gravity that you've got in there and that line, is there sort of an awkwardness, when you have something as a lighting designer, if you have something that's out of line, there's a frustration, or there's something wrong, and it can be quite disturbing. Does that happen if you ended up having those oranges like you had for the ABC, and one is not in that line? Does that cause a sense of not just stress, but sort of an awkwardness because it's not sitting in that line? So is there an emotional feeling that something's not lining up, like we saw that orange looked like it was illuminated because it was off outside of that realm?
Yeah, an interesting question. I think it might, from a painter's point of view, it might just have a different. It might create a perception of something different physically going on. So that, say, for example, you had a light sort of halfway up that was more saturated than you expect, that can make the object look like it's translucent, and so the light is shining through the material, you see, and so you can therefore get an unusually strong color in the half lights where the light is just sort of grading through, you see. So that's sort of my answer from a painter's point of view. But I think I'm obviously talking mainly about the fundamental science of the color here, and hoping that each individual designer, and there's 8 or 10 different kinds of designers at least, will find their own sort of application of it.
Yeah, no, because I just thought that would be really quite interesting. When something's off and you can't quite put your finger on it, and that might be that hasn't got that sort of commonality to that line that you've been showing on your examples. But thank you very much, David.
Yeah, so that's really just in the simplest possible situation, and then all sorts of complications can come into play there. Yeah.
Thank you for that question and for your answer, David. I do have one here in the chat as well. Sue Spriggs has asked if there's a specific app that you could recommend, or something beyond those resources, for finding color or color finding.
I've come across a few recently. Would you like to send me an email, and I'll send? How about I'll put my email in the chat anyway. How's that?
Great, that would be fantastic. I will ask if there's any other questions while David is doing that as well. Please do raise your hand or pop it in the chat. Thanks. Fantastic. Thanks, David. I'm sure Sue will follow up with you on that one as well. If there aren't any other questions, we perhaps will finish up the session, but I just, on behalf of the SANT, but the broader community as well, wanted to thank you, David, for your time and your expertise. It's an incredibly fascinating thing to see colour displayed and, to be honest, demonstrated in such a scientific and kind of beautiful way through all of those different graphs. So it's incredibly important that we engage with this research, and that research again comes back out into that really organic intellectual way. So thank you very much. Thank you everyone who has joined us online tonight. This recording will be available for you to rewatch again and dig deeper into all of those big details that David canvassed for us tonight. Thank you very much. We'll look forward to you joining us again for another talk in our colour series a little bit later on in the year with a new speaker. But very much again, thank you, David, and thank you everyone. Have a great evening.
Thanks, Nathan. Thanks, Georgina. And let's do some other questions there. But please, anyone's welcome to email me at that email address, and I'll give you the information then. Thank you.